This is invited already. Rahul is well known for his works on many different parts of physics, including quasi-periodic Schrödinger equation, surface problems, heart tissue, critical problems, and of course turbulence. Today he will talk about Navier-Stokes framework for multi-phase fluid flows, laminar, turbulent, and active.
Yes, thank you very much, Subhadip, and thank all the organizers, especially Guillaume, for inviting me here. It's a great pleasure to be here. Now, this is a meeting on boundary layers. So when Guillaume invited me, I said, look, I don't do boundary layers, but there are lots of interfaces in Cahn-Hilliard-Navier-Stokes. And he said, oh, that's fine. So with your permission, I will tell you about what you can do with the Cahn-Hilliard-Navier-Stokes framework for multi-phase fluid flows. I've had the benefit of collaborating with several people on this topic. John Gibbon, who does the mathematical things, Nadia, who's now in Germany, Kiran, he's in Nice, Vishwanath and Vasant are in Bangalore, Prasad, who was here last week, Noirita, Pal, Anupam Gupta, and Dario Vincenzi, and support from all these agencies who have very kindly supported our work over the years. We've published some non-zero number of papers. I will not go through all of them. If you want an overview of what we have done, we recently published this perspective article in Journal of Fluid Mechanics, and you can see the title is the same as the title for the talk. It has more things in that paper than I can possibly cover in the talk, but let me see what sorts of things I can cover. So here's an outline, an introduction, a generalized Cahn-Hilliard-Navier-Stokes equation for binary, ternary, and active fluid flows, illustrative results. If I have time, some mathematics, and if I have a little more time, some machine learning. So binary fluid flows, as all of you know, abound in nature, okay? The standard picture that people like to show is that of a schematic diagram of a cloud, which has droplets of various sizes, typical raindrops, moisture droplets, and so on. To understand this from first principles is a problem that will take several decades, but people do many things, parametrization and so on. So at least it tells you that in many physically relevant flows, we have more than one phase, and in between the two phases, there is an interface. There are other examples, for example, droplets of oil in water, a beautiful object that was found, I think, in 1933 by Hughes and Hughes. If I'm not mistaken, it's called an antibubble. It has a shell of low-density fluid inside a high-density fluid that's obviously unstable, and it forms a little bump at the top. There are ternary fluid flows. For example, compound droplets, so phase A, phase B, phase C, have been used for modeling white blood cells. Then there is a bubble passing through an interface. I'm not sure I'll have the time to cover that, and a Faraday instability on a floating droplet. Now there are active fluids. I won't play the movies because they will just take away time unnecessarily, but later if someone wants, I can play them in the question and answer session. So this is a movie of a droplet of Bacillus subtilis, and it forms a single spiral vortex. And if I were running the movie and you see this dense suspension of E. coli inside a spherical droplet, then the center of mass executes a random walk. Again, these are multi-phase flows, but they're active in a sense, which probably all of you know, but which I will make precise in the Cahn-Hilliard-Navier-Stokes context as we go along. Now, if you talk to fluid dynamicists, you know, there's such a wide spectrum that there are many different views, which are well stated in this important overview by Balachandar and Eaton. says dispersed multiphase flows are distinguished from other kinds of multiphase flows, such as free surface flows. In dispersed multiphase flows, the evolution of the interface between the phases is considered of secondary importance. Processes such as droplet or bubble breakup and agglomeration do indeed alter the interface between the phases. However, in the context of dispersed multiphase flows, one accounts for the interface between the dispersed and carrier phases in terms of a particle size spectra without considering the detailed evolution of the interface. This is what is done traditionally in the engineering literature. So I will do just the opposite. I will restrict myself to systems in which the different phases coexist in thermodynamic equilibrium, which I will cover like a statistical mechanician later, and where it is necessary to account for the surface tension and the breakup or coalescence of droplets of these phases. And we really must combine then the theoretical methods of statistical mechanics and fluid dynamics. I don't know whether you can see all this, but probably it's all right. Take a coarse-grained view of this slide, all right? So if I were teaching binary fluid mixtures, I would start with a model of magnetism, an Ising model, which has up spins and down spins. And in the low temperature phase, below the Curie temperature, you will have two coexisting phases, all up or all down, all right? And those are the two phases. They coexist along what a statistical mechanician would call a first order phase boundary. And the order parameter, which is the magnetization, jumps as you go from the upspin phase to the downspin phase. Now, why did I bring this up when I'm talking about fluids? Because there is a well-known mapping of the Ising model onto a lattice gas. You can always write up as 1 and down as 0. Okay, then the down becomes the low density phase and the up becomes the high density phase. This is the so-called lattice gas model. And then the two coexisting phases are high density and low density, all right? Now, how do you proceed beyond that? To do the equilibrium statistical mechanics, you have to get the free energy. The free energy is too hard, except in 2 dimensions in the absence of a magnetic field, then Onzaga solves it. But at a practical level, everyday things, you do what's called mean field theory. So you say, I don't know, you can't see any of this, doesn't matter. You say that...
You can see some of it there. So if you use the cursor...
Right, okay, fine. So you make the Curie-Weiss approximation, a spin at this side sees a mean field because of the others, and then it becomes a variational problem where basically you have energy and minus the entropy, and then you minimize with respect to the order parameter. Now, this is on a lattice. You don't want to do lattices. You do a gradient expansion, then you get this Landau-Ginzburg free energy functional, okay? So it's got a local part which depends on the order parameter phi. Phi is like the magnetization. So large and negative values of phi are low density phase. Large and positive values of phi are high density phase. And then there is this grad phi whole squared term, the coefficient of which is the surface tension. So this is elementary theory of surface tension and interfaces in a statistical mechanics course. Now you want to look at the time evolution of this interface. Then you have to go to what would normally be called time-dependent Ginzburg-Landau. That's given here as oh, I can't get my cursor now. All right, doesn't matter. You look wherever you get the Cahn-Hilliard equation. Delta phi by delta t is m del squared. The functional derivative, did that go away? Stop sharing. Stop sharing by mistake. Excuse me, sorry. These are the problems of a hypersensitive. 1 minute, I will share again.
Well, you have 1 hour, 30 minutes, so no
Oh.
need to rush,
All right, okay, good.
including questions, of course.
Why is it not sharing? Everything is frozen here. Should I join the meeting again or?
Oh, you seem to be online. Let's do it.
You can join.
My computer is frozen.
The only thing is I'm going to give you a memory stick. The switch computers.
One second. Something happened. Wait. It's all right. PM? Some luck? No, it's not all right. Same thing is on. Yep. You're right.
Same service. Maybe you log out for
It worked.
Which one? Is this the volume? This one.
Or you'll still have time for coffee.
Yeah. No, it has to respond something.
About the resources.
Fill this. Sorry about this. I don't know why it's doing this.
We're in safe hands. Our chair has a propensity to do jokes.
That's what the chair is becoming known for. I should take up stand-up comedy. We had movies and
No more. Well,
still happening.
they're copied.
Till that Put it back there.
Hmm?
You don't need your computer anymore.
No.
Okay, given my reputation, quick story. Long time back, Rutherford was giving a talk in the Royal Society when he was very young. And it was a demonstration and something got stuck. So then for a moment, Rutherford said, look, guys, go and have some tea and it will be fine when you come back. That's when Lord Kelvin said, this guy will go a long way. Done? This is heavy with data.
See.
Okay, we are back.
Okay, thank you. This way. Oh, so ignore the movies, don't worry.
Okay, so we are back. Just reminding the students, please ask questions.
Anytime.
Copy from.
Yeah, I didn't copy it, but it's all right. Yeah, that's fine. That's fine. Okay, back to my tutorial on Khan Hilliard, just plain Khan Hilliard. All right. So to derive this sort of an equation starting from statistical mechanics takes some zero number of steps through kinetic Ising models with a so-called conserved order parameter. Okay, so the conservation here shows up in this extra del squared outside the functional derivative of the free energy. So if you Fourier transform, you will see the k equal to 0 mode will not evolve in time. All right, and this is the natural thing to do when you are working with fixed amounts of fluid. Okay, so the fluid A is conserved, fluid B is conserved. And this is the celebrated equation that goes back to the late 1950s, developed by Khan and Hilliard, and it's used to study things like spinodal decomposition and phase separation in binary fluid mixtures. Well, binary mixtures, excuse me. So now if you want to make it a binary fluid, then of course you must add Navier-Stokes, which of course I don't need to introduce to this audience. And when you put all of them together, you get Khan, Hilliard, Navier-Stokes. All right? Just press V. Oh no.
That's the normal French answer.
All right. So here is some more background. So if you had a homogeneous binary fluid mixture, it undergoes what is called spinodal decomposition. You know, try to mix them up, which is what happens at high temperatures. You suddenly cool down to a low temperature below the consolute point at which they mix, and then it phase separates into these red and blue patches. All right. And at the first level, you can get it from this so-called Landau-Ginzburg free energy functional. V phi is the local part that is typically taken to have a double well form. Okay. So it has minima at phi equal to +1 and -1. And the positive phi is A rich and the negative phi is B rich, or high density and low density. Okay. And note the important thing, phi changes continuously as I go from the phase A to phase B. And people who teach statistical mechanics often give this as a homework problem to illustrate the simplest mean field theory of an interface between two coexisting phases. So if you look at that local potential V phi, those are the two minima. You enforce boundary conditions so that it is -1 at -infinity, +1 at +infinity, and you get this nice tangent hyperbolic profile, which you can do actually analytically. So this is the mean field theory of an interface. There's no Navier-Stokes yet. Okay? Yes?
You can do it analytically only in 1D, right?
Only if you, yes, right. So that's why I made it 1D. So I'm assuming that in all the d-1 dimensions transverse to this, it's the same. Okay, so now the equation that will occupy us for the rest of this talk, the Cahn-Hilliard-Navier-Stokes equation. So this part is Navier-Stokes, all of you know this. And I have a row A and a row B in instances where you have gravity acting downwards. You can have a density difference times the gravity. This basically comes with a new dimensionless parameter called the Atwood number. All right. There's incompressibility and there's good old Cahn-Hilliard, but with an advection term, u dot grad phi. The u is coming from Navier-Stokes, and here is the back reaction of the field phi onto Navier-Stokes. So the field phi in the language of fluid dynamics is an active scalar. It affects the flow even as the flow affects it. Okay. Unfortunately, the terminology has been muddied a bit after the advent of active matter. So they use active in a different way, and I will get back to that later in the talk. So other important parameters, psi is the width of the interface, and here is the bare surface tension, which comes in from the free energy functional that we had earlier. Now, some comments. This is a theory with a diffuse interface. Now, experimental measurements show that typical interfacial thicknesses are a few nanometers. Okay, there are some estimates here. But so many of the engineers will get very upset with the Cahn-Hilliard-Navier-Stokes equation because they say, look, your interfaces are too thick. But there is a way of checking and taking the sharp interface limit. And in some cases, we have checked with different numerical schemes. But I should also say, while I'm giving you the downside, I should give you the upside, which is you do not have to track a moving interface on which you have to enforce boundary conditions. Kai Schneider knows how difficult that is. Here, phi is taking care of everything. All right? It's all in the equations. But of course, you pay a price. Price is that there's just not one Reynolds number. There's a Reynolds number, there's a Peclet number, there's a Bond number, which is a dimensionless combination of gravity and surface tension. In other settings, there's an Ohn-Sorge number, which is some dimensionless combination of viscosity and surface tension. There's a capillary number. There's a Kahn number, which tells you how thick the interface is. And there is a Weber number, which is the inverse of the surface tension. So depending on which physical situation you're looking at, you know which number to concentrate on.
They already depends.
No, I mean, of course, obviously not, because Weber has 1 over sigma, so does Sorg, etc. So it really depends on which system you're looking at. It's most convenient to use one or the other. But there are several.
There's a nice PDF page called Dimensionless Numbers in Fluid Mechanics.
Yes.
We put this on a chart and you can move from one to the other.
Is that right? Including binary fluids?
Yes, cut number and so on.
Okay, good. Thank you. All right, so we know how to simulate all this. I will skip this because I'm sure all of you know how to do pseudospectral simulations and do them well. All right, so if you have this framework, what can you find? So let me give you some illustrative results. This is an old paper with Noirita Pal, Prasad, Anupam, and myself. So you can, in particular, look at a droplet in a turbulent flow. So here are two pictures. These are 2 different droplets. This is when the surface tension is high. This is when the surface tension is low. So when the surface tension is low, you have a very floppy droplet. Otherwise, it's sort of roughly circular. This is a 2D simulation. And you can characterize the deformation of this droplet by taking a ratio of the perimeter of the droplet calculated from the phi equal to 0 contour. So this scalar field phi gives us a convenient definition of the droplet boundary. You take the phi equal to 0 contour and you non-dimensionalize it with an undeformed droplet of equal area, and you plot it versus time. And you see it's a very, very spiky series. It's, you know, those of you who grew up with Menevo and Srinivasan will say, obviously that's multifractal, and you wouldn't be wrong. And I asked my student Melita at that time to check, and sure enough, you can get an F versus alpha spectrum out of it, which tells you that these droplets in a turbulent flow show multifractal deformations, which somehow had never been noted before. You might say, well, if it's turbulent, it better be multifractal. But here is a specific characterization of that multifractality, right? I'm sorry?
Can you say again what is the quantum factor?
This deformation parameter which I defined, which is roughly the perimeter. If you follow the perimeter as a function of time, it has huge fluctuations, especially at low surface tension. I mean, qualitatively not a surprise, but here's the quantitative characterization of that. All right. Now, I told you about coarsening. Now, in the statistical mechanics, if you want to get rid of, the system phase separates. Okay, eventually in equilibrium, you will get only one flattened phase between the A-rich phase and the B-rich phase, right? So if you want to mix the 2 phases, what you do is you raise the temperature. But now you have coupled Navier-Stokes, so you can do something else. You can crank up Reynolds in some way, and then the turbulence will mix up the 2 phases for you. This is called coarsening arrest in that field, all right? So here, what is changing over here is at late times when coarsening arrest has occurred, okay? And then this is at RE equal to 124. And what you can see is that the domain sizes decrease as we increase the Weber number. I will remind you that Weber number is inverse of the surface tension. So here also you can try to characterize this state, which is now would have been phase separated in the absence of Navier-Stokes, but because of Navier-Stokes, you have 2D turbulence and you churn it up. And this also shows up, I mean, turbulence people are very familiar with energy spectra, E of K. Similarly, when you have a binary fluid system, you can add another spectrum to your bag of things that you look at. This is normally called S of K, which is the spectrum of the phi field, phi of K, phi of minus K. that also spreads over many ranges of K. And you can also make a plot of a sigma times some coarsening arrest scale. This S of K allows you to define what is called a coarsening arrest scale. This is very reminiscent of the integral scale we would define in fluid dynamics with E of K. Just if you replace this by E of K, you will get an estimate of the integral scale. So this tells you the typical droplet size in the churned up state. And there's an old Hinser criterion, which I will not go into here, but it is consistent with the dependence of the on the surface tension, for example. There's a 3/5 bar, and that line actually shows that our simulations are doing that. Yes. Well, yes, the most important difference is that 3D is much more expensive to simulate. That's why I'm not showing you 3D, but occasionally we do have 3D results. Yes, you have a question?
Well, I guess one in 2D, there's no capillary breakup.
Right, I mean, 2D also, I mean, if 2D left to itself, Navier-Stokes might have an inverse cascade. Then you have to worry about the dependence on the energy injection scale and so on. But this was done in a forward cascade regime, if I remember correctly. But I would have to look up the details. Okay, so yeah, I think, no, sorry, there was an inverse cascade. I said something wrong. So this is where the energy injection was. You can look at many things, but in the interest of covering a lot of ground, let me skip the details here, but I'm happy to answer questions in the question and answer session. Okay, now let me talk to you about this beautiful thing called an anti-bubble, which goes back to the 1930s, if I'm not mistaken. Oops, can you see very much here? All right, okay, let me just show you. Here is an anti-bubble. So let's see. So this is the thin sliver of light phase, which is shown in red, and the blue is the background heavy phase. And what happens is that this south pole, if you like, of the film thins, and you find a little bump coming up at the top, and eventually it breaks, it becomes a single bubble, and it goes up. Okay? And you can follow, of course, the vorticity field also, which you cannot see very well. Perhaps the next one is better. So as far as I know, this is the first theoretical description of an anti-bubble, the full spatio-temporal dynamics. And here we did do 2D and 3D. And this lower one is actually not from Kahn-Hilliard Navier-Stokes. To address the engineer, these were done with volume of fluid also, and qualitatively everything is the same, even quantitatively. Okay, so here you don't see my movie. I can show it to you later offline. And this is a 3D simulation. So here is the experimental picture given to me by my former student, Chirag Kardel. So you see this little bump at the top. So the bottom thins and the bump begins over here, and then it becomes a bubble, and it just goes up all the way. And this Kahn-Hilliard Navier-Stokes gives you a completely natural description of this phenomenon. This is volume of fluid, so we won't go into it. And here is a plot which you cannot see, but to show you that it's not only pictures, you can get, for example, the droplet breakup time as a function of the bond number, which was this dimensionless combination of gravity and surface tension. And you get plots which are completely consistent with experiments. All right. Now, in some recent work with Nadia and Dario Vincenzi, we looked at a type of low Reynolds number turbulence. Now, sorry, what did I do? All right, low Reynolds number turbulence, I guess the most well-known example is polymeric turbulence. I mean, Truba knows that very well. You have one more parameter in the problem. In the polymeric problem, you have the Weissenberg number. And even though the naive Reynolds number is small, the Weissenberg number is large, and that drives the fluid to turbulence. So here we will show you another example of low Reynolds number turbulence, which is driven not by the inertial term, but basically by the interfacial fluctuations, which can be enhanced by lowering the surface tension. So you begin with some arrangement like this. So low density, high density, or the other way around. And you can plot over here. I mean, this sort of a flow in the fluid dynamics literature is called a cellular flow. It is imposed by a forcing term, which is periodic in space and time. Now, you can so-called melt this crystal by increasing the amplitude of the forcing. That would be conventional melting of such a cellular flow by conventional turbulence. Now, what we will do is we will keep the Reynolds number so low that in the absence of these interfaces, this cellular flow would maintain its integrity. Instead, we will lower the surface tension, and then lo and behold, this will melt. Melt, I'm using in the sense of a good old-fashioned solid-state physicist. Disordered, if you like. And it really is melting in the sense that if you were to take a Fourier transform of this periodic structure, you would get what a solid-state physicist would recognize as Bragg spots in reciprocal space, which will get completely washed out when you go to this flow. So it's a low Reynolds number turbulence driven by a decrease in the surface tension between the two fluids. Okay, so there we go. All right, so here are the types of reciprocal lattice plots I was going to show you. So when it is close to a crystal, you get nice Bragg spots. When it's not a crystal, it's just washed out all over reciprocal space. If you look at time series, they can either be periodic or stationary or chaotic. So actually, whereas the conventional, take equilibrium melting, take good old copper. You heat it, you melt it. There's a single phase transition, which is first order, at which you will lose your Bragg peaks. Here in these systems, and we have found this in whether it's driven by turbulence or this, and actually Pat has done many studies in the 2D MHD version of this problem. I will mention that towards the end. This is not a single transition. It's a real mess. That's why I typically stay away from transition, because it can go from periodic in time, but not periodic in space, or quasi-periodic in time, etc. So there's a whole bunch of transitions. I wouldn't even be surprised if there's an infinity of transitions. But at the level at which we can follow it, we have a finite number of transitions. The low noise state is a well-defined crystal imposed by the forcing. The high noise state is disordered completely. And in between, you can get many combinations of order and the lack of it, either in space or in time or both. So you can really get spatiotemporal chaos. Now, let me, since active matter is developing very rapidly, let me give you one example of active turbulence. Okay? Yes.
Say you have possibly an infinite that's even for one type of force and the same. Should you, have you played the game of trying different types of force?
No, I must confess we have not done it. But okay, yeah. I wouldn't be surprised, of course, this is not a proof. I'm not a mathematician. I'm not saying I have proved there are an infinite number. I have checked various things. We have found 4 or 5 given our experience, and there have been other people who used to study transition like Bruno Eckhart, etc. They had also found the whole for some other unrelated problems. So, these boundaries between such states, if we call them that, my first guess would be this, if you like jargon, it's a fractal basin boundary. So there's a huge amount of reentrance and this and that. Okay. So you can either explore it and you'll find more and more depending on how much you do. But of course, if you're a really tough mathematician, you will prove it's a fractal basin boundary. But that's not one of my strengths. I can't prove it.
But I was more leaning towards, do you have some forcing? Would have certain characteristics that would lead to an order again.
I don't know. I have to look. See, at the simplest level, what you want to make is what a statistical mechanician would call a phase diagram. So on the vertical axis, you would have Weber number, which is inversely related to the surface tension. On the horizontal axis, you would have Reynolds, or if you're really working with fixed forcing, it might be better to have some non-dimensionalized Grasov. So you could map, if you had enough computer resources and so on, the full boundary between the completely ordered and the completely disordered. When people do this in the polymeric fluids literature, and then if you just go along the Reynolds axis, you eventually go to what would be called a drag reduction region, where the polymers have a drag reduction thing. And then if you do it via Weissenberg, then you go into something called elastic turbulence, and then there's a crossover between the two. In fact, Gruber has recently, I don't know whether he talked about it, studied elastic turbulence like that. So I think it's better to do non-dimensionalized, but even when you do non-dimensionalized, it will still be quite complicated. That's what I'm saying. Yes?
I think or
Well, it's not only it's really the surface tension. Yes, but it can either favor or the formation of interfaces. And if you have lots of interfaces, they churn up the fluid. Okay, but it's really a combination. I'm not saying it is this term or that term. It's all there. But sorry, your comment?
I say both.
Yeah, probably both.
Agreeing with you.
Yeah. Okay. All right. So if you allow me, I will go ahead. How much time do I have? Well, tell me.
10 minutes.
10 minutes? Okay, fine. Okay, active coarsening arrest. So we just did this free energy functional with one scalar order parameter phi. Okay, so now I'm just calling it psi. All right, and we had thought this would be a good model for contractile swimmers, Chlamydomonas reinhardti, CR for short. Okay, we'll see. So what we have over here is this sort of a term, which is good old Pan-Hilliards with the advection from the Navier-Stokes. This is Navier-Stokes. Now I've written it in a funny way. I've written it as the curl of this sigma psi, which is this term. If you put it all together, this is what you would have got for Pan-Hilliard Navier-Stokes if this coefficient zeta epsilon had been exactly sigma. the surface tension. By allowing it artificially to be different from sigma, you can make it active in the sense that this is not any more derivable from a strict free energy function. Okay, because if you did it from there, then you would get sigma. And this is a model that goes back to Michael Cates, etc. They called it active model H. In the old critical phenomena literature, what I'm calling Kahn-Hilliard Navier-Stokes, by people like Hernberg and Halperin, they called it model H. Therefore, this term active model H. And the claim is that this parameter zeta, if it is greater than 0, it is for extensile swimmers, and if it is less than 0, it's for contractile swimmers. All right? And they showed they had a slightly different model. They typically look at Stokesian flows, but they have some external noise. So it's a stochastic PDE, and that's what drives what they call motility-induced phase separation, which was suppressed in one case and not the other. So we are going to do the same thing, but with this contractile thing. And then we will see if this leads to turbulence on its own. And of course, I wouldn't be giving the talk if it didn't. So, so these are pseudo grayscale plots. And as the activity increases, there is an activity-induced turbulence, if you like. All right? And that turbulence does exactly the same thing I told you about earlier. You take Kahn-Hilliard Navier-Stokes, the phase separation is suppressed by the turbulence. That's conventional turbulence. This is activity-induced turbulence, again within the Kahn-Hilliard Navier-Stokes type of framework. Okay, and there is a vorticity field here. Yes?
It's
the thickness of the interface. Yes, so right. So if you get all the parameters right, it will work out.
So here, do we have phase separation of the active particles into one of the two phases? Is that what?
So it's not only active particles, it is this. I have a scalar field now, psi. If it is large and negative, you have fewer, lower swimmer density, and if it's large and positive, it's more. Yes, sorry.
Tune the activity, as
Yes.
it were, of the swimmers. Can you dial what amounts to a hint scale of your choice?
Yes, absolutely.
You can.
This is my next slide.
You would suppress the
Next
the
slide.
coarsening.
So this is the phase field spectrum. Okay, and with the phase field spectrum, I can define a length, just like we had defined the earlier arrest length, which we related to the Hinze length. That's what Pat has in mind, and you can do the analog of that. And if that activity parameter is 0, you get full scale coarsening. For those who know coarsening, this L of t should increase as t to the 1/3, which is known as Lifshitz-Lozov. But now with this activity, it asymptotes to a constant, and indeed it goes down with activity. And if you define a Reynolds number, the Reynolds number goes up with activity. Okay, you can do various spectra, etc. I will leave that to question and answer whenever someone wants it. All right. Now you can do ternary fluid flows. So I have 5 minutes.
Yes.
Okay, so what you can do with 2 fluids, if you're a good statistical mechanician, you can do with 3 fluids. We had 2 minima now. In a sort of Gibbs triangle, now you will have 3 equal minima if you want to get 3-phase coexistence, which requires 3 concentrations, C1, C2, and C3, but with the overall constraint that they sum up to 1, because we are working with fixed concentrations. So you can write down all the equations. Believe me, it works. You couple this to Navier-Stokes, and you can use it to study many things. So let's look at it to study droplet coalescence or the coalescence of lenses. Often people find, you bring two droplets together, a little neck will form, all right? Or if you bring two lenses together, that requires three-phase coexistence, green, brown, and blue. And there's a height of the neck, which evolves in time. And you can do the vorticity also. Don't worry about that for the moment. But the experimental data, if you look at it, the height of the neck as a function of time has two parallel regimes. One is t to the 1, and the other is t to the 2/3. And the t to the 1 is in the viscous regime, and t to the 2/3 in what they call the inertial regime, where these mergers lead to some degree of turbulence. And again, I'm happy to report that with our Kahn-Hilliard-Navier-Stokes three-phase simulations, we can get the crossover from these two regimes. Yes, sure. Okay, so you can do it in 3 dimensions also. Here we have done both 2 and 3. So this is just a qualitative slide just to show you we've done it. Okay, and it does induce some degree of turbulence, which you can monitor by seeing the evolution of the energy spectrum. All of you can see that energy is distributed over at least 2 decades of wave number. Okay, let me, what should I do? Let me not do self-propelled droplets, but we have, a very nice paper, at least I think it's very nice, all right, where we put in 2 order parameters, and you actually get a little droplet that forms with a little umbilicus here, and it slowly propagates through the simulation domain. Okay, and if you increase the activity too much, then it just sort of more or less like a heart undergoing ventricular fibrillation, which you don't want. It just jiggles all around, and then you can characterize that. Okay, so, but I don't have enough time to cover this now. Later, if anyone's interested, I can cover it. And again, the droplets have multifractal interface fluctuations, much as they did with conventional turbulence. Okay, in a few minutes, I will try to tell you about transport barriers. Those of you who study layering in oceans and whatnot, I learned all this from Pat Diamond and the great schools he's been organizing. These layering leads to transport barriers. So the only way I understand at my low level, a transport barrier is to see whether this interface actually prevents Lagrangian particles from going out or staying inside. So the top view is a group of Lagrangian tracers. They've been just put in the flow with no barrier, nothing. So it's not two-phase. Okay, and then they spread like Lagrangian particles. But here, it's actually put all inside a droplet of one phase. And this is a small droplet, and this is a bigger droplet. And as the simulation proceeds, the droplet moves around, its center of mass moves around, but the Lagrangian tracers find it very hard to go out of the droplet, okay? And we can actually characterize this by looking at the number of particles that stay inside the droplet up to time t. And that has an exponential decay from which we can extract a time, and that time increases the power of the radius of the droplet. Now again, if you give this talk to engineers, they will say, no, particles will never come out of this thing. So then you have to take the limit of thinner and thinner interfaces and higher Reynolds numbers, and then it does what you expect. At high Reynolds number, particles come out, and if it's very thin, they don't come out. I will not cover the rest. There's lots of things, but I just want to end with a list of problems that I would not have covered even if I had time. So there are so-called quasi-compressible Cahn-Hilliard-Navier-Stokes models. I will not cover those. There are intriguing links between the two-dimensional Cahn-Hilliard-Navier-Stokes system and 2D MHD, I think explored best by Pat's group. So any hard questions you have, I'm sure he can field those. We have, for simplicity, considered phases with equal densities and equal viscosities, except when we did the antibubble where we needed the density contrast. But this can be changed easily. This is not a big problem. There has been some interest in studying Cahn-Hilliard type partial differential equations and curved surfaces by the group of Voigt. One can do that also here. I have not done it yet. And then the latest fashion in town is non-reciprocal systems. Non-reciprocal Cahn-Hilliard. Some papers have been published already, and we have a lot of unpublished work on turbulence and non-reciprocal Cahn-Hilliard-Navier-Stokes, but I will not cover that today. But with that, I would like to thank you for your attention, and I'm happy to answer any questions you have now or afterwards. I'm here till the morning of the 17th. Thank you.